In this video, we're going to look at how to analyze simple diode circuits using the analysis by assumed states approach to determine the state of our diodes and therefore the voltages and the currents in the circuit. So you can imagine if you're given a circuit like this, you might be asked to calculate V, you might be asked to calculate I, and that's not possible unless you know the characteristics and the state of D1 and D2. So how are we going to figure that out? Well, first you'd need to decide which diode model you're going to use. If given this as a question, that would usually be specified within the question. So if we start here with the ideal diode model, we'll take a look at how we'd run through the analysis by assumed states. So with the ideal model, we know that if our diode is in reverse bias, it will just be treated as an open circuit, and if it's in forward bias, it will be treated as a short circuit. So to begin our analysis, we simply choose a starting assumption of those states, and we work through to look for any inconsistencies on our circuit analysis based on that assumption. So one way to do that would be to make a simple table of your diode states and whether or not the circuit remains consistent when the diodes are set up that way. So that should make more sense as we work through the example. If we start with the assumption that D1 and D2 are on, then we need to analyze the circuit and see if there are any inconsistencies when our diodes are in those states. So let's first take a look at D1. If D1 is on, so it must be in the forward bias, then we replace it with a short circuit with our ideal diode model. So our 1 volt will transfer as a short circuit directly through to V. So V at this node here would equal 1 volt. But if D2 is also on, that would also be replaced by a short circuit, which would mean we'd have 2 volts directly placed on this node voltage. So straight away there we can say we have an inconsistency. So is that circuit consistent? No. Now what about if we try D1 on and D2 off? So once again, if D1 is on, then we know we have a short circuit here and our V would equal 1 volt. Now if D2 is off, that means it must be under reverse bias and will be treated as an open circuit. But if we look at our circuit, we see we have 2 volts on the left side here of D2 and 1 volt on the right hand side. So that diode must be under forward bias. So that's inconsistent with the need for it to be under reverse bias for it to be off. That diode must be on. So we make another assumption. D1 is off, D2 is on. So if D1 is off, we would have an open circuit here, and if D2 is on, then we have a short circuit through D2, which places our voltage at 2 volts, as we just have a direct line to this voltage here. Now is that consistent with D1 being off? For D1 to be off, it needs to be in reverse bias, and that means the voltage on the right side must be higher than the left. We have 2 volts on the right, 1 volt on the left, so that's consistent. So we can say yes. So that tells us the state of the diodes. And given that information, we now already have the node voltage V equal to 2 volts, and we could easily calculate the current I, as we have a 7 volt drop across this 2 kilo ohm resistor. So we can just apply Ohm's law. And once you've found a consistent state, that would be the solution to the circuit. So you don't necessarily have to work through all of the other states beyond that condition. So we can also do this analysis using the constant voltage drop model which would do here on the right hand side. So in this case, if we have reverse bias conditions, then we still have an open circuit, but if we have forward bias conditions, then we effectively have a voltage source of VF, and in this example we'll say that's 0.7 volts. So if we make another table of our diode states, and once again we work through and we look for those inconsistencies and try to find the consistent condition. So as before, we'll first assume that both diodes are on. Now in this case, if the D1 diode is on, then it must have a 0.7 drop across that, which means that the voltage of V is going to equal 0.3 volts, because we have 1 minus this 0.7 volts across the diode. If D2 is also on, then we have a 0.7 drop across there, meaning our voltage would be 1.3. So once again we have an inconsistency here, and these two things can't occur at the same time. So that would be a no in the C column. Now if we go to on for diode 1 and off for diode 2, then once again we have 0.3 volts for diode 1, but now we're saying that this will be an open circuit for D2, and for that to be the case it must be under reverse bias, which means in this case that the voltage on the right hand side must be higher than the left, and that's certainly not the case. As we can see, we have 2 volts on the left, 0.3 on the right, so that diode must be on. So once again, inconsistent. So if we try D1 off and D2 on, now in this case D1 we're assuming to be off, so that would be an open circuit at D1, and D2 we're assuming to be on, so that would be a voltage source of 0.7. That gives us a V of 1.3 volts. Now we can see that the 1.3 volts is higher than 1 volt on the left there, so it's consistent that this diode would be under reverse bias. D1 will be under reverse bias and therefore would be off. So here once again we can say this solution is consistent, just as with the ideal case. So in this scenario, both our ideal and our constant voltage drop diode models gave us the same diode states that were consistent, in that being that D1 is off and D2 is on. But they do lead to different values for our voltage at this node here and for our current I. If you remember from the ideal model, we had 2 volts at V, and therefore that would be 7 volts dropped across that 2 kilo ohm resistor. And in the constant voltage drop model, we have 1.3 volts at V, and therefore 6.3 volts dropped across that 2 kilo ohm resistor. So that would lead to a different value for that current. And we can expect that the constant voltage drop model, if we're using a silicon diode, will give us a much more accurate answer for the value of V and for I than the ideal model.